So you have taken the practice exam, one of my old exams, like it was a test, and now you're going to go through and you are going to grade your work. So the following says we're looking at the limit as x is approaching 3 pi fourths of 2 cosine x. So all we're doing when we're looking at limits, first thing that you want to do is you want to do direct substitution. And so doing direct substitution here, I would get 2 cosine, and I'm replacing x with 3 pi fourths. So now I just need to go through and evaluate what cosine of 3 pi fourths is. So recall, if we're looking at the angle 3 pi fourths, this angle gets us into the second quadrant, and our reference angle would be pi fourths. Cosine is negative in quadrant 2, and so this would give us 2 negative of whatever cosine of pi fourths is. Well, cosine of pi fourths is root 2 over 2, so this would give us back cosine of 3 pi fourths is negative root 2 over 2. Notice that our 2 cancels in the numerator and denominator, and we're left with just negative root 2. So if you're in my class and you're grading your exam, give yourself 1 point if you got this correct. Give yourself a half a point if you got some of it correct, and just 0 if you didn't get anything correct. Let's just do that based off of every problem. 1 point if you get it correct, a half a point if you have some knowledge but did not get it correct, and 0 points if you didn't get it correct. So the following limit, we have x is approaching 0 of this rational function, 6x to the 5th minus 8x cubed. This is all over 9x cubed minus 6x to the 5th power. So again, we would first start with direct substitution, but I noticed right away, if we do direct substitution, we have 6 times 0 to the 5th minus 8 times 0 cubed. That's just 0 in the numerator, all over 9, 0 cubed, minus 6 times 0 to the 5th. That's also 0 in the denominator. If we get that form 0 over 0, this is an indeterminate form, which means it doesn't tell us anything about the limit, and we need to go back and we need to manipulate our function. And so if possible, factor it. And in this case, we can factor. So notice in the numerator, we can pull out an x cubed from both of those terms. So if we pull out an x cubed from both of those terms, notice that we get back 6x squared minus 8 all over, and then in the denominator 9x cubed minus 6x to the 5th. Those both also have an x cubed in common that we can factor out, and that would give us back 9 minus 6x squared. Our x cubes cancel in the numerator and denominator. And now when we go in and we do our direct substitution, we have 6 times 0 squared minus 8 all over 9 minus 6 times 0 squared. So this would give us back negative 8 all over 9. So the limit as x approaches 0, and that function is negative 8/9. Part C, the limit as x approaches 0 of 1 over x minus 4, then plus the fraction 1/4. And both of those terms or groupings are all over x. Again, if we did direct substitution here, we get a negative 1/4 plus a 1/4 in the numerator, which gives us 0. All over, plugging in 0 for x in the denominator, we get 0. So again, we have this indeterminate form. So we want to go back and we want to manipulate this. So since I have fractions within a fraction, the way that I want to deal with this is we want to clear our fraction within the fraction. So let's multiply by our fancy one, and that fancy one that we're choosing is the least common denominator of these fractions within. And so these fractions within, this x minus 4 in the denominator and the 4 in the denominator, my least common denominator would be 4 times the quantity x minus 4. So I want to multiply this both to the numerator and denominator. And when we do that, our fractions will cancel out. So when I distribute this 4 times x minus 4 to the 1 over x minus 4, our x minus 4s are going to cancel, leaving us with 1 times 4. And then we have a plus. So now distributing this 4 times the quantity x minus 4 to 1/4, our 4s are going to cancel. And we're left with 1 all times x minus 4. And the denominator, let's just keep it in factored form. So this is the same thing as 4x all times x minus 4. Just rewrote the order a little bit. So let's simplify our numerator. So I have 4 here plus x minus 4. That's my numerator, all over 4x times the quantity x minus 4. Notice in our numerator, our 4's cancel. So we're left with a common factor now in our numerator and denominator of that x. So we can simplify by canceling out that x. So we're left with 1 in the numerator, all over 4 times the quantity x minus 4. So doing our direct substitution now, plugging in 0 wherever we see an x, we get 1 all over 4 times 0 minus 4. So this is equal to 1 over 4 times negative 4, which is equal to negative 1 over 16. So part D. Part D says we have the limit as x is approaching 5. In the numerator, we have x minus 5. In the denominator, we have the square root. Underneath the radical is x plus 4. And then outside of the radical, we have minus 3. Again, if we did direct substitution, I notice right away that I'm going to get 0 over 0. In the denominator, I have 5 minus 5, which is 0. I'm sorry, that's the numerator. In the denominator, I would have the square root of 5 plus 4, which is the square root of 9, which is 3. 3 minus 3 is 0. So I get that indeterminate form 0 over 0 again. So I need to go back and manipulate this. If you have radicals in that rational expression that you're taking the limit, then we want to multiply by the conjugate of that radical and whatever that other term is. So in this case, we're going to multiply by another fancy one. And this time our fancy one, we are going to use this more. Well, the conjugate of the radical, square root of x plus 4 minus the 3 is square root of x plus 4 and then plus the 3. Whatever we do to the denominator, we also want to do to the numerator. So bringing down the limit, because we haven't evaluated it yet, as x is approaching 5, we have in the numerator x minus 5 times the square root of x plus 4, and then plus 3, all over. So for the piece that we're multiplying through the conjugate, basically I'm using the fact that if I have a binomial a minus b times the binomial a plus b, the conjugate of each other, then that's the same thing as a squared minus b squared. So technically, if I FOILed that out, I would have x plus 4 quantity squared minus 3 squared. So let's simplify our denominator, rewriting our numerator, bringing down the limit. So I have a limit as x goes to 5 of x minus 5 all times the square root of x plus 4 plus 3 outside the radical. And this is all over, well, squaring a square root cancels the radical, leaving us what underneath the radical, which is called the radicand, in this case, x plus 4 minus 3 quantity squared. 3 quantity squared is 9. So I notice right here, if I simplify the denominator a little more, notice that that reduces to x minus 5. So now I have a common factor, x minus 5, in that numerator and in the denominator. So I'm going to cancel those out. So all I'm left with now in the denominator is just 1. Which I don't need to write that anymore then. So really, I'm just taking the limit as x is approaching 5 of the square root of x plus 4. And then outside of the radical, I have plus 3. So now doing our direct substitution, once we do the direct substitution, we no longer write the limit. And so we have the square root of 5 plus 4. That's under the radical. Outside of the radical, we have plus 3. So this is equal to the square root of 9 plus 3. Square root of 9 is 3, so 3 plus 3 equals 6. Okay, so for an exam, you should be able to take the limit as we're approaching some value. If you get that indeterminate form, we looked at the 3 cases that you might see where you have to either factor it, get rid of the fractions within the fractions, or if you have a radical and you get 0 over 0, then multiply through by the conjugate of that. So moving on, oops, I guess we are not done with this. So now we have part E, the limit as x approaches 0 of sine squared of 2x all over x squared. So I want to use the fact that if we have some limit as x is approaching 0, we call of sine of some argument, let's just say, call it ax, all over the same thing as what our argument was for sine, ax. We saw that this was equal to 1. So sometimes if we have a limit and we have sine in there, we want to manipulate this. Again, if I had done direct substitution, and that's really where I want to start, is I would have gotten 0 over 0 because sine of 0 is 0 and 0 squared is 0. So let's rewrite this. I see that I have sine squared of 2x. Sine squared I can rewrite as the product, right? This is the same thing as sine of 2x all times sine of 2x. And then let's rewrite this x squared as x times x. So the only thing that I'm missing here to use that rule above is that I need technically a 2 here and a 2 here. So I multiply 2 times 2 is 4 in the denominator. So that means in order to keep this equivalent, I need to multiply 4 to the numerator. And so now we can kind of break this up if it helps you as 2 separate fractions multiplying together. And now as we look at the limit as x is approaching 0, and that sine of 2x over 2x, that goes to 1. This one goes to 1. So all we're left with here is the 4 times 1 times 1, which is equal to 4. So the next limit, we have the limit as x is approaching infinity of the quantity negative e raised to the negative 2x power. And then outside of the exponent, that term, we have minus 5. So let's kind of manipulate this and rewrite it a little bit. Remember, if you have a negative exponent, we can rewrite that piece with a positive exponent by changing the position. If it's in the numerator, which in this case it is, we can put it down into the denominator. So I have the limit as x is going to infinity of negative 1 all over e raised to the 2x power. And then the minus 5 outside. So recall, if you have 1 over a number that goes to infinity, that goes to 0. Well, if I take e raised to the 2 times infinity, recall e to the x or e to the 2x looks similar to this function. And so as I'm going off to infinity, my denominator is blowing up and going to infinity. So this piece, -1 all over e to the 2x, this piece goes to 0. And so we're left with 0 minus 5, which is equal to -5. So the next question we have in front of us is a piecewise function. And we want to find the limit as x is approaching 1 of this piecewise function. If the limit does not exist, explain why. So notice that our equations change. If I'm to the left of 1 less than 1, I'm using that first equation, x over 2 plus 9/2. If x is bigger than or equal to 1, I'm using x squared minus 6x plus 10. So since I'm changing equations at 1, then I want to look at my limit on the left-hand side. So I'm looking at the limit as x is approaching 1 on the left-hand side, which means I'm choosing values close to 1 but less than 1. So if I'm choosing values close to 1 but less than 1, that tells me I need to use my first equation, x over 2 plus 9/2. Now going in and doing that direct substitution wherever we see an x, we're going to get this 1 over 2 plus 9/2. So this gives us 10/2, which reduces down to 5. So the limit as x approaches 1 on the left-hand side gives us 5. Recall, in order for a limit to exist, the limit on the left has to equal to the limit on the right. And so now let's look at the limit as x is approaching 1 on the right-hand side. So if we're plugging in values close to 1 on the right-hand side, we're choosing values of x which are bigger than 1. And so for this piecewise function, if a value is bigger than 1, it tells us to use our equation 2, x squared minus 6x plus 10. So doing direct substitution now, we have 1 squared minus 6 times 1 plus 10. Simplifying this, we get 1 squared is 1, minus 6 times 1 is 6, plus 10. So 1 minus 6 is -5, plus 10. This gives me 5. So left-hand side limit equals right-hand side limit. So that tells me that the limit does exist, and the limit as x is approaching 1 of f of x is equal to 5. Problem number 2 is another piecewise function. We have our first equation for f of x is x squared minus 5x minus 6. That quantity is all over the quantity x minus 6. We're going to use this if x does not equal 6. And then our second equation is 3k plus 2. This is if x is equal to 6. So we want to find the limit as x is approaching 6 of f of x. So again, we want to see what's happening on the left-hand side, and we want to see what's happening on the right-hand side. So if we are looking at the limit here, as x is approaching 6 on the left-hand side, so something that's smaller than 6, that tells me that I need to use my first equation because it's not 6. 6 on the left is approaching 6, so getting very, very close to it. So if we do direct substitution here, I get 6 squared minus 5 times 6 minus 6 all over 6 minus 6. So I have 36 minus 30 minus 6 all over 0 and get 0 over 0. So unfortunately, that's that indeterminate form. So let's go back in here and let's simplify this. And so let's do that by factoring. So I notice that my numerator can factor. Bringing down my limit as x is approaching 6 on the left. Factoring my numerator, x squared minus 5x minus 6, thinking of two numbers that multiply to give me -6, but add to give me -5. That would be a -6 and a +1, all over my denominator of x minus 6. I can cancel like factors. So now I'm just plugging in 6 into the expression x plus 1. And doing so, I get 6 plus 1, which is equal to 7. So I do the exact same thing now, looking at the limit as x is approaching 6 on the right-hand side. Well, if I'm coming into 6 on the right-hand side, I'm choosing values which are close to 6, but bigger than 6. And if x doesn't equal 6, which I'm getting close to 6, but not equal to 6 necessarily, that tells me that I use, again, that first equation. I would do direct substitution again. I would get the same thing as I got above, that 0 over 0. So I would need to factor it. I can factor it just like I did before. So technically now I'm just evaluating this limit as x is approaching 6 on the right of x plus 1, which again is 7. So we can say that the limit as x approaches 6 is equal to 7. Part B, on the same question, it wants to know what value does k need to be in order for that limit as x approaches 6 of f of x to equal f of 6. So if we looked at f of 6, this is telling me to go into my piecewise function. When x is 6, tells me that I'm using my second equation. And so this would be 3k plus 2. Notice there's no x in there. So when I go in and I plug in 6 wherever I see an x, this is equal to 3k plus 2. So I want to know, when is my f of 6, which we just said was 3k plus 2, equal to my limit as x is approaching 6 of f of x, which we just found above was equal to 7. So we're trying to find out what k needs to be in order for this to be a true statement. It's a linear equation. We want to isolate that variable k. So first thing we want to do is move the 2 over so we can subtract 2 on both sides. Subtracting 2 on both sides, we get 3k equals 7 minus 2, which is 5. Divide through both sides by 3, we get k is 5/3. So in order for the limit as x approaches 6 of f of x to equal f of 6, that k value needs to be 5/3. So we basically just created it that this piecewise function would be continuous at x equals 6. Okay, so moving right along, we're looking at now number 4. So let g of x be a given function. G of x equals f of x plus a if x is less than or equal to 0. The second equation is 3 minus b cosine of x if x is greater than 0. Where a and b are constants and f of x is equal to 1 minus x squared, show g of x is continuous at x equals 0 if a is 1 and b is 1. Okay, well, let's just rewrite this a little bit. So I can rewrite, so g of x is equal to f of x plus a. Okay, well, f of x is 1 minus x squared plus a. And it told me in here to let a be 1, so plus 1. This is if x is less than or equal to 0. And then let's write down the second equation. We have 3 minus b, but it told me b to be 1. So 1 times cosine of x is just cosine of x. And this is if x is greater than 0. So I'm going to just rewrite this a little bit, simplifying my first equation. I have 1 minus x squared plus 1, so 1 plus 1 is 2. So I have 2 minus x squared if x is less than or equal to 0. And I have 3 minus cosine of x if x is greater than 0. So to show that g of x is continuous at x equals 0, well, I know that my function 2 minus x squared, if my domain was all real numbers, that's continuous everywhere. I also know that 3 minus cosine of x is continuous everywhere. But since it's a piecewise function, we're worried about, is it giving me the same limit as I approach the left and the right of where it's changing equations, which in this case is 0. So I need to look at the limit as x approaches 0 on the left-hand side, which means it's values which are less than 0, which means I'm using the first equation there. Doing direct substitution in this, I get 2 minus 0 squared, which is 2. So let's look at now the limit as x is approaching 0 on the right-hand side of 3 minus cosine of x. So doing direct substitution here, I have 3 minus cosine of 0. Recall cosine of 0 is 1, so I have 3 minus 1, which is also 2. So since the limit as x approaches 0 on the left is equal to the limit as x approaches 0 on the right, I'm almost done. The limit exists. So limit as x approaches 0 of g of x exists, that equals 2. G of 0. So if I went in and plugged in 0 where I saw an x, well, it tells me in this case, if x is 0, this tells me to use the first equation. So this is equal to 2 minus 0 squared, which is 2. So g of 0 exists. And the last thing that needs to hold in order to be continuous there is that the limit also has to equal that g of that value that we're looking at the limit, which it does. The limit as x approaches 0 of g of x does equal g of 0. So those three conditions hold. Therefore, this is g of x is continuous at x equals 0. Okay, so question number 5. Question number 5. So we're given that f and g are continuous. The function h is given as h of x equals f of g of x minus x. The table below gives us the values of the function. Explain why there must be a value for t for 1 is less than t is less than 4 such that h of t equals -2. Okay, so looking at this. So again, we are given that h of x is equal to f of g of x minus x. I want to know that there's some value between 1 and 4, such that h of t is equal to -2. So let's look at the following. Let's look at what is h of 1. Well, h of 1, according to this, let's go back to our equation. This is the same thing as f of g of 1 minus x, which is 1. So let's simplify this. F of, well, g of 1. So we're going to look at our table. When x is 1, our g of x is 3. So g of 1 is 3. So I have f of 3 minus 1. So again, I'm going to go back up to my table and look at what is f of 3. So now I'm going to my table. I'm looking when x is 3. What is f of 3? F of 3 is -3. So I would get f of 3 here is -3 minus our 1, which is -4. So now let's look at what is h of 4. So same sort of reasoning here. I'm just going to go in and plug in 4 wherever I see an x in my function. So this is f of g of, I see an x there, replace it with 4, minus x, but I'm going to replace that x also with 4. So using our table, let's first look at what is g of 4. So I'm going to go over here, figure out when we have x is 4. Looking at my row for g of x, g of 4 is 2. So I'm going to look at f of 2 minus 4. So now let's go to when x is 2. And I'm looking at f of 2. So f of 2 gives me back 8. So this here is 8 minus 4. So 8 minus 4 is 4. So here's the main point. If f and g are continuous, then there's a rule that the composition also has to be continuous. So I know f of g of x is continuous. I know x is always continuous. So by the intermediate value theorem, I'm going to call it IVT, intermediate value theorem, since h of x is continuous, and h of 1 is equal to -4, our y value is -4, and h of 4 is 4, there has to hit all these values, y values, in between -4 and 4. And so if I'm hitting all the y values between -4 and 4, then I must also hit a y value of -2. So therefore, h of t equals -2. Therefore, there must be a t such that there must be a t that's in the interval, so contained in the interval between 1 and 4, such that h of t equals -2. Okay, so that was the first portion of the exam. When I gave this exam and I was teaching this calculus class, it meant 4 days a week. And so they didn't have enough time to take a full test, and I was split it up into 2 separate days. That's why there's a part 1, part 2 here. You guys are not going to have it split up into 2 separate tests. And so let's move on. You should have done this also. And so let's go through the key of the second part of the practice test that you took. And so this says, let f of x equals 1 over x. We want to find the instantaneous rate of change of our function. So we want to find the derivative here. So we want to look at the limit as h approaches 0 of this f of x plus h minus f of x all over h. So doing direct substitution, if I plug in x plus h wherever I see an x in my original function, I have 1 over x plus h minus f of x, which is 1 over x, all over h. Unfortunately, we go in here, do our direct substitution, we get that indeterminate form of 0 over 0. So we need to manipulate it. We're going to manipulate it by multiplying by our fancy 1. That fancy 1 is the LCD of the fractions within, which in this case is x, all times x plus h. All over. Do something to the numerator. We also have to do it to the denominator. So now when we do our distribution, our fractions are going to go away within our fraction. So 1 over x plus h times the quantity x plus h is cancel, leaving us with just an x there. Minus, so distributing that to 1 over x, and this time our x's would cancel, leaving us with, be careful here, you should put parentheses, x plus h. All over, and let's just keep it as x, h, times x plus h. So limit h goes to 0. Notice when I distribute my negative sign inside the parentheses in the numerator, I have x minus h. So x minus x cancel. I'm left with negative h all over xh times the quantity x plus h down there in the denominator. Again, if I plugged in 0 for h, I get 0 over 0, but I notice that I have a common factor of h in the numerator denominator. I can cancel that out, leaving us with a limit as h goes to 0 of negative 1 all over x times x plus h. So now go do your direct substitution, plugging in 0 wherever you see an h. We get back negative 1 all over x times x, which is negative 1 over x squared. So that's the instantaneous rate of change, which is also known as our derivative, which we can write as f prime of x. So that was part A. Part B, find the instantaneous rate of change of f of x at x equals negative 4. Before we do that, I just want to talk about it really quickly. If it didn't tell you to use the definition of derivative here, we technically could have used the shortcut that we have been learning, the general power rule. We could, in this case, use, if we wanted to, the quotient rule. I would technically rewrite f of x before I took the derivative. So this is the same thing as 1 over x is same thing as x to the negative 1 power. Now, if I use my general power rule, bring our power down front, negative 1, subtract 1 from my exponent. So negative 1 minus that 1 would give me negative 2. Notice I get the same thing as negative 1 over x squared. So you could use what we just learned recently to check the work if you were supposed to use the definition. So all we need to do for part B is find the instantaneous rate of change at x equals negative 4. So all we need to do is plug in negative 4 wherever we see an x in our derivative function. So if I go in there and plug in negative 4, I would have negative 1 all over, I see an x. So I'm going to replace that with a negative 4 inside the parentheses, which means I need to look at negative 4 times negative 4, which is positive 16, but I have a negative 1 over a positive 16, so negative 1/16. So the instantaneous rate of change at x equals negative 4 of f of x is negative 1 over 16. Part 2, use the intermediate value theorem to show that there must be a 0 of f of x equals x cubed minus 125 on the interval 4, 6. So we want to evaluate that function, f of x, at the end values of our interval. So we want to look at what is f of 4. So if we go in here and plug in 4 wherever we see an x, we have 4 cubed minus 125. So 4 cubed, 4 times 4 is 16, 16 times 4 is 64 minus 125. don't have a calculator right in front of me, so let me just do this really quickly. So it gives me negative 61. Now let's look at f of 6. So we go in and plug in 6. Wherever we see an x in our function, we have 6 cubed minus 125. Well, 6 cubed, well, 6 times 6 is 36. And then 36 times 6. So that's 216 minus 125. Which gives me back 91. So notice we're opposite signs. F of 4, I have a negative number. So I have a y value that's negative 61. F of 6, I have a y value of 91. X cubed minus 125 is a continuous function. And so as we're going from x equals 4 to x equals 6, we must be crossing the x-axis there. So by the intermediate value theorem, IVT, there must be a 0. At least 1 0 between x equals 4 and x equals 6. Okay, so our next problem, 3, use the epsilon-delta definition to prove that the limit as x approaches 5 of 2x minus 4 is equal to 6. Okay, so we need to choose some delta such that we know that the absolute value of x minus a in our case is 5, is less than delta. And we know that our function, f of x, which in our case right here, f of x is 2x minus 4, minus what the limit we're approaching, which is in this case 6, has to be less than epsilon. So we're going to let that hold true. So our goal here is to manipulate what's inside our absolute value to look like what is inside our absolute value up here. So let's first simplify. So we'll, inside the absolute value of 2x, we'll have negative 4 minus 6, so that's minus 10, is less than epsilon. I notice that I can factor out a 2 from the 2x minus 10. So absolute value of 2 times the quantity x minus 5 is less than epsilon. Well, absolute value of a product is equal to the absolute value of the first times the absolute value of the second. So absolute value of 2, I don't really need the absolute value there anymore because absolute value of 2 is 2. And so we could divide both sides by 2. And so notice now we have what we wanted. We have the absolute value of x minus 5 is less than epsilon over 2. So we want to choose our delta to be that epsilon over 2 here. So we just use the epsilon delta proof to show that that would be true. Okay, so part 4, show why the limit as x goes to 0 of the absolute value of x over x does not exist. Well, if we did direct substitution, I would get the limit as x approaches 0, the absolute value of x over x. This would be the absolute value of 0 over 0 is 0 over 0. We got that indeterminate form that doesn't tell us anything. So we need to go back and manipulate this. Technically, the absolute value of x, that is a piecewise function. We can define, so let's say f of x equals the absolute value of x. Well, if x was positive or greater than or equal to 0, then whatever we plugged in the absolute value, we'd get the same thing back. It would just be x. If x was less than 0, though, in order to find the absolute value of it, so if I take the absolute value of a negative number, basically I'm taking the negative of that negative number to make it positive. So this would be negative x. And so let's look at the limit as x is approaching 0 on the left-hand side of this absolute value of x over x. Well, if I'm looking at this absolute value of x and I'm plugging in numbers that are less than 0, then I'm basically looking at the limit as x is approaching 0 on the left. That absolute value of x, I'm going to write it as negative x over x, which simplifies to -1. So if I'm looking at the limit as x is approaching 0 on the left of -1, this is equal to -1. So now let's look at the limit as x is approaching 0 on the right of the absolute value of x over x. I get 0 over 0, so I want to manipulate it. If I'm choosing values that are greater than 0, that tells me that I'm going to use, this piece. So I have the limit then as x is approaching 0 of x over x, that reduces to the limit as x is approaching 0 on the right of 1, which is equal to 1. So since the limit as x is approaching 0 on the left-hand side of the absolute value of x over x does not equal the limit as x is approaching 0 on the right-hand side of the absolute value of x over x, the limit as x is approaching 0 does not exist. Okay. Again, the limit exists only if the limit as x approaches a value on the left equals the limit as x approaches 0 on the right. Part number 5, last question. Let f of x be continuous on some interval a, b, and let c be a value between a and b. In your own words, explain the difference between the average rate of change of f of x on that interval a, b, and the instantaneous rate of change at x equals c of f of x. Okay, so it really varies in how you're going to explain this. If I'm looking at the average rate of change on the interval AB, basically I'm looking at the slope. So average rate of change. Okay, I'm going to look at the slope of my secant line. So that would be looking at what is f of b minus f of a all over b minus a. If I'm looking at the instantaneous rate of change, I'm looking at what's happening. What is the slope of my function f of x exactly at x equals c? And the instantaneous rate of change well, I could write that as f prime of c. That would be equal to the limit as h goes to 0 of f of c plus h minus f of c all over h. So the average rate of change is giving us the, it's like, basically we're looking at, lots of words right now. Basically that's giving us the average of what the slope would be. If we found the slope at every point between b and a, x equals b and, or x equals a and x equals b, looking at the average, that would give us that value, where the instantaneous rate of change is giving us the slope at one particular value on the graph. So hopefully going through those solutions was helpful. So for my class, go ahead, grade your work, put your score on the top of the page, and then submit that assignment to Canvas for me. Your exam for my class is on Thursday. If you're in my online class, it's Thursday. You can either come in and take it via Zoom, 8 a.m. to 9:50 a.m., or you can take it 6 p.m. to 7:50 p.m. If you prefer to come in and take it in person, you have two options. I need to know that you're coming in and taking it in person so that I can have the test available for you. But one case is you can come in on Wednesday from 10 a.m. to 11:50 on the Yuba College campus, room 1019. Shoot, that's not true. Wednesday, you can come in and take it 10 a.m. to 11:50 a.m., but that would be room 849. I'll post this in the announcement. Thursday, if you want to come in and take it in person, same time, 10 a.m. to 11:50 a.m. That's room 1019. If not, I will see you via Zoom, webcams on, taking the test Thursday, the 16th, either morning or evening slot. I don't allow makeups on tests for any reason. So you want to make sure you get in there and take the test. If you have accommodations through DSPS, you want to talk to them, set up an appointment, let me know when your appointment is. That way I can make sure that they have the exam for you and ready for you when you go in to take it. Look forward to seeing you next week. Take care. Bye. Well, maybe bye. Let's see, let's turn off the recording. Okay, see you next week. Bye.